I'm sure things are ticking over in your head for what you can do with this, okay? The whole point of this is to think about, okay, I can't actually put in x equals 1 into here, can I? I can't just go there and tell me where it is. Unlike here, where you can literally, like, the reason why you get 2 is because if you put 0 into here, 2 just pops out, right? But as you can see, you can't always put in the value and you can still approach something. So for instance, here, what would I do? This numerator I can factorize, right? The limit as x approaches 1 of x plus 1x minus 1. Okay? So because I can see here, right from the first line, that x is not actually defined, the function is not defined at x equals 1. I can disregard x equals 1. X can't be equal to 1, right? That first line tells me there's a restriction, okay? So therefore, this guy I can cancel, right? These two can disappear, okay? They can be taken out of the factor, right? So I'm getting this. Now I'm at a point where I actually can, just like here, I can pop in the value that I'm trying to approach, right? As x approaches 1, this thing is going to become closer and closer to 1 plus 1, right? Which is 2, okay? So therefore, what does that actually mean? Well, let's graph this thing. Let's graph this thing. Let's even think back to when we were talking about oblique asymptotes, when we were talking about polynomial division and so on, right? Degree 2 divided by degree 1. What result are you expecting? Degree 1, right? It's going to be a straight line. It's a linear function. In fact, it's this linear function with one crucial difference, right? Hold on, did I do this right? X plus 1? Yeah, I did? Okay. Where is x equals 1? X equals 1, there's my intercept. X equals 1 is over here, right? So there's some point over here where, just like we said from the very first line, the graph is not actually defined. There's a little tiny infinitesimally small hole there, right? You can't put in x equals 1, so there's a hollow circle, right? But it doesn't mean, like, I can still approach that value. I can approach it from above, I can approach it from below, and sure enough, I'm getting closer to 2. I can get closer and closer and closer. I can get as close as I like, I just can't get 2 itself, right? Because I can't actually put in 1, right? So therefore, this idea here of approaching a limit, even though I can't actually evaluate it, that's why limits are valuable, okay? I can actually evaluate something that I can't evaluate. I can see what it's approaching, even if I can't actually get there, okay? So now I'm going to give you my formal definition. Well, it's not mine. It's a well-known definition. And I'm going to put it right underneath my other definition. Yes, people who've watched Mean Girls are having this running through their heads. If you want for reference, I'm giving you basically a kind of rewording of what's on page 268 of your textbook. They give you a definition, but I'm not a huge fan of it, but that's okay. It's not that bad. Okay. So here comes all of the formal stuff, right? Limit as x approaches a.
Is that a definition?
Okay, yep, so here comes my definition. It's formal, which is why I'm using all this notation, and that's why I'm putting it with the other one, right? Okay, if I say the limit as x approaches some number for this function, if I say that limit is b, that means I can pick some value of x such that I can get arbitrarily close to b. Okay? Let me write that out and then we'll unpack it. Okay? Means we can substitute some value into that function and get arbitrarily close. Arbitrarily to. Okay. So for example, let's think about this guy here. Let's think about this guy here. Okay? This limit is 2. And the reason why is because if you want to say, how close would you like to get to 2? You're like, I'd like to get within 0.1 of that spot there. Okay? If you're like, you want to get to within 0.1 of 2, I can do that. I can find an x value that'll do that. All I have to do is say, okay, 0.1 equals that thing, and then I'll solve. And there's a solution to that. It'll be like, you know, what did I want? You might get 1.01 or 0.99. Okay, so you have an x value that will get you within 0.1 of there. Okay, I should have said 2.1. That's where I want to go. Within 0.1 of that actual point. You're like, no, I don't want to 0.1. That's really far away actually in terms of my accuracy of measurement. I want to get within 0.001 or within 0.00001. Or they have this they call this in fault tolerance, they call this sigmas. So for example, if you want something to be 99.99999% certain, they call that sigma 5 certainty, okay? So that means I would have to be within 0.0000002, I guess. That's how close I would be to be 99.99999% certain, okay? Well, guess what? There's an x value you can pick that will get you that close to 2. And because you can get as close as you like, we say that's what the limit is, okay? If, for example, I can't actually get that close, there's somewhere earlier I have to stop, then that earlier place you have to stop, that's the real limit, okay? In this case, I can get as close to 2 as I like. Over here, I can get as close to 0 as I like. For example, you're like, tell me, is there a place on this function where I'm going to be equal to 0.000000001? And the answer is yes, there is. You just need to go far enough. You'll find it. It's there, right? And if you want to add more zeros, you can do that too. You just have to go further, okay? So this is the limit if you can find some value such that when you put it in, you'll get however close you want to be to that actual value, okay? Like I said, I prefer to say it's just the value that you approach because that's just a much more common sense way of saying it. But later on, as you'll see, it's like, well, you know what? Over here, I rubbed it off. Over here, right? This is y equals x plus 2, right? You're not actually approaching 2. You actually get there, don't you, right? I do more than just approach. Like in an asymptote, right? I can actually get that value, which is why this thing I put a box around is more intuitive, but in terms of like a rigorous formal definition, it kind of doesn't hold up as much water as the other one does.